Welcome back to my videos. I'm gonna start us off with a little bit of a dad joke. What happened to the frog when he parked next to the fire hydrant? He got towed. There's your dad joke to start off. Next, we're gonna jump right into the questions. So first things first, it's asking us explain how the resting membrane potential of the cell membrane is established. So I drew a little cell here, and I drew three different things. I drew a potassium leak channel, which is over here. I drew a sodium-potassium ATPase pump, and I drew negatively charged proteins. So what's going to happen is the potassium over here, 3 of them are going to go out, and 2 potassium are going to go in. So you're going to have a larger concentration of sodium on the outside and a larger concentration gradient of potassium on the inside. Now, due to this concentration gradient, potassium is able to leave the cell through potassium leak channels and negatively charge, and that will help in establishing RMP. And then negatively charged proteins are here as well to also establish negativity. Now, the reason why I drew this down here is to resemble what's happening. So basically, whenever the potassium or any charged particle is leaving or entering into a cell, only the positive charge or the charge in which it has is going to move, such as this potassium leak channel. We're going to call this a potassium leak channel, that a potassium leak channel. What's happening is that potassium is going to leave, so just that potassium leaves, but that chloride then leaves a negative charge on the outside. And because the charges want to find each other, you can't just have a charge on its own. You're going to have this negative on the outside, on the inside, and that positive on the outside. And that will then cause the inside of your cell to become more negative. Now this is happening with everything in each case. So each time that potassium leak channel is happening, that's going on. Whenever the sodium is leaving, that's happening there as well. So the sodium ATPase pump contributes a little bit to the negative 70 RMP. And then the negatively charged proteins contribute a little bit, but the main contributor is the potassium leak channels. Yep, so as I said, potassium leak channels are the main contributor, and then the sodium-potassium ATPase contribute a little bit. The inside of the cell is negative compared to the outside. Next question we have up is what properties / characteristics of the cell membrane account for the resting membrane potential's development? Here, I'm showing us, I just wrote a few things to help us remember some things that I already talked about. So the 3 properties or characteristics are gradient, such as there's a higher, I think I already wrote this over here actually. We have a higher concentration gradient of potassium inside the cell due to those sodium-potassium ATPase pump. So that gradient is one of the factors contributing to that. Another factor that is also helping with that is whenever the cell loses those potassiums as they come out, the negatives are going to be out there. And so that negative charge is the electrical gradient. And because the potassium is positive, the negative charge is going to want to attract that. So it's going to fight itself a little bit, which is why it doesn't continually get more negative, like negative 100 inside the cell, is because that electrical gradient, once it gets strong enough, it fights the concentration gradient as well. And then to continue with that is, it's the concentration gradient also fighting along with that. Here, and just showing that the cell membrane is selectively permeable. Some ions pass through easier than others due to different leak channels, such as like the potassium leak channels, having the concentration gradient being able to flow through more, while there are a lot less sodium leak channels. So they don't really contribute all too much to the charge of the cell at all. Next up, I talked about this a little bit already, but the sodium-potassium ATPase pump maintains the concentration gradients of sodium and potassium, which are essential for RMP. So those concentration gradients can then fight the electro gradient. And then just so we know, there's a higher concentration of sodium on the outside of the cell because it's pushing it out. So sodium is going to want to flow in whenever an action potential happens, which we'll talk about here in a little bit. And last but not least, that those negatively charged proteins also contribute a small amount to the overall negative charge of the cell, and they're not permeable to the cell, so therefore they're just sticking around. And then we also talked about gradients, electrical, and chemical. Next up, we have our question that says, what conditions or factors affect the resting membrane potential's magnitude/size? Include a brief description of the Nernst equation and driving force. So we talked a little bit about some of the factors that affect it, but we're just gonna touch on a little bit more. And so here I'm just letting you know that you cannot have an accumulation of charge in the body. It's just a separation of charge. So basically what that is saying is, you have your cell, you can't just have a bunch of free-floating negative ions being accumulating within the cell. You're going to have what's going to happen is you're going to have those negative charges being separated from their positive charges, but not accumulating themselves. All right. So next thing I'm going to discuss is the Nernst equation a little bit here. So first things first, we show that the ion, which X equals the ion, as you can see here, is equal to the negative 61.5 over the charge, which if it's a potassium, it's a +1. If it's chloride, it's going to equal -1. Multiplied by the log of the concentration of the ion inside the cell and out of the cell over the concentration of the ion out of the cell. And this is done for each specific ion. So this way we can start to calculate what is being affected and how things are working. So some of the things that we have done is just some quick calculations and examples of them. If you have 150 potassium inside the cell and 5 potassium outside the cell, then we're going to get a negative 90.1 millivolts. And moving to the sodium, if you have 10 outside the cell and 140 in, we're going to have 69.9 millivolts. And chloride, if you have 20 inside the cell and 100 inside the cell, we're going to get negative 48.58. Remember to take into your account of the negative here. and that's only considered for the ion. Now let's take that and make it a little bit and show you how how you can get the voltage of the membrane itself. Now what you're going to do is you're going to take that negative 61.5 and then multiply it by the log of the sodium inside, the concentration of the sodium inside multiplied by its permeability, and add each ion that plays a role in that as well, such as potassium inside the cell with its permeability, chloride outside the cell and its permeability, and calcium inside the cell and its permeability. And then you're going to put that over the inverse of what it is, such as a concentration of sodium outside the cell times its permeability plus the concentration of potassium outside the cell plus the concentration of chloride inside the cell and plus the concentration of calcium outside the cell, always all of them multiplied by their own permeability. And then this will help give us the voltage of our membrane. And as we do that, we can then find out the driving force of each ion. So the driving force of each ion is this equation here. Your driving force is going to equal to the voltage of the membrane minus the ion, the millivolts of the ion. Such as, let's do that sodium here. Negative 70, which is the RMP, minus 69, which is the sodium, equals negative 139. Now, we have to remember that you always put the driving force inside the cell. So, as we put the driving force inside the cell, and you have a channel open here, which way is the positive sodium going to flow? That's right, inside the cell, because it's a negative force. So that sodium is going to want to flow inside the cell as it's a positive charge. The positive will want to flow. An easy way to remember this is the positive will want to flow towards a negative. Next, I just gave a couple more examples here, such as if you have a positive 10 charge inside the cell with potassium, it's going to push potassium outside the cell. And just to demonstrate the difference driving forces has on different ions, chloride, if you have a positive plus 10 inside the cell, it's going to actually draw chloride inside the cell because that negative charge wants to flow towards that positive driving force. While if it's negative, the good way to think about it is that negative ion will flow out away from that negative driving force. Think about it as negative repelling negative, just to help cement it in your mind. Another thing to keep in mind is driving force is also shown on the graph here. You take the concentration of the ion, which is 69, which is up here. So, and then you place it in accordance to where RMP, the VM, is. And then you take that calculation, and that will find you your driving force. So as you can see, the driving force here is much larger than the driving force of the potassium here. And this here is just showing you the driving force of potassium as well. If you do have a channel that is competing for one of these, the driving force that the ion that has the higher driving force is going to be the one that wins. Luckily, we have permeability that keeps those driving force from, that keeps different channels from allowing one in or another. And then this is just showing you some correlation with the equation here, such as if you increase intracellular sodium, you're gonna affect the VM by making it more positive. If you increase the sodium out, it's gonna make it more negative. And then just showing you with each stimulus. If you increase potassium in, more positive, increase potassium out, more negative, increase chloride in, more positive, increase chloride out, more negative, and so on. Now that we've gone over that, I'm just going to talk about this gradient here for a little bit. So once the gradient is moved enough, the chemical gradient will attract the charge more than the leak channel flowing through. And so it's basically just going to, that's what I was talking about earlier with that negative charge battling with the positive charge on the outside, the electrical gradient battling with the concentration gradient, the chemical gradient. And so these are the different factors that are affecting the resting membrane potential, because each of these different ion millivolts and the total voltage of the membrane using all of these, which this total voltage is known as the GHK equation. That will help you find the membrane voltage. Next thing we're going to do is discuss this third question. In part 2 of this essay, discuss the action potential. List its characteristics. Describe the events that take place during a typical action potential, including a description of the various phases, rising phase, falling phase, after hyperpolarization, relative refractory period, absolute refractory period, and for each phase describe the actions of the channel involved in the ions and the ion's currents. Compare and contrast a graded potential with an action potential. So first thing I'm going to do here is go over this graph here. Number 1 here is just showing RMP. Number 2 is showing a stimulus, and I'll go over this more in depth. Number 3 is showing where the action potential is taking place at threshold. Number 4 is showing the depolarization. I'll go ahead and write that on the graph here. Number 5 is showing the peak. Number 6 is showing the repolarization. Number 7 is showing an event happening with the voltage-gated potassium channels. Number 8 is showing hyperpolarization. And then number 1 goes back to resting membrane potential. And we have our absolute refractory period, which consists of depolarization and repolarization. Then we have our relative refractory period, which includes hyperpolarization. So that's what we wanted to just focus on there a little bit. Now I'm going to go into each one a little bit more in depth. So number 1 is just showing us resting membrane potential. Remember, we talked about that earlier, what contributes to that. Number 2 is some sort of stimulus that's causing a graded potential, a depolarization event, and ligand gate, which cause ligand gated channels to open. Notice this is important. It's ligand gated, not voltage gated. Due to that, it's going to depolarize that cell. And with this being said, before I move on to number 3, if this graded potential, aka this slight depolarization, is not strong enough to hit threshold, it is not going to cause an action potential. It's just going to reset back to RMP. So if you don't reach it, you're not getting nothing. That's this all or none principle right here that I'll talk about here in a little bit. The third event right here, oops, not right there, but the third event right here is talking about the graded potential, the depolarization being strong enough to reach threshold, which opens up voltage gating potassium channels. And because there is a strong concentration gradient from potassium outside the cell being higher than the concentration of the potassium inside, it's going to flow in really fast. Now, before I move on with that, I'm going to quick sketch a voltage-gated sodium channel for you. So right here, oh, that was a big eraser. Right here, you're going to have a something similar to a spring made up of amino acids. And as this spring is on the bottom, it's pushing a gate right here closed. This here is called your activation gate. And so something needs to occur in order for this to be activated. And I'll talk a little bit more about why this is being kept closed. This here is your inactivation gate. To prevent flow after this gate opens. So the amino acids here on this activation gate have positive charges that are keeping it pushed down, keeping this spring-like amino acids pushed down. So as there's more positives on the outside and more negatives on the inside, that's going to keep that gate pushed down. But as we see with our depolarization event, it is starting to take away some of these negative charges. And it's going to start taking away some of these positive charges. Therefore, that spring will then allow this gate to open up. So this spring will move more upwards, and it'll open up, allowing the sodium to rush in really fast. So that's what's happening at number 3. So as the sodium is rushing in really fast, this inactivation gate here, up there, is going to swing shut really fast, so that way you have a lot of sodium that made it inside the cell, causing an even higher depolarization. But this happens throughout the cell, so you'll still have some channels open, but they're closing up. So like this one hasn't quite reached that yet, but the majority of them are closing up. And then once you reach the top, this peak here, and this depolarization is also known as your rising phase. So just going through here, as sodium rushes into the cell, the inactivation gate and voltage gated sodium channels close the opening. They start. And then at the 5, at the peak, right here, that's when all the inactivation gates of voltage gating sodium channels are closed. So you won't see any more open ones like you do in 4 a little bit, every now and then here and there. Every single one is going to be closed. And then you also see, another thing that you'll also start to see is at around 3, that I didn't quite mention, is the voltage gated potassium channels. Start to open. But they open slowly, which means they're not really opening at a speed where it can rush in all too much. So that sodium concentration gradient is going to be the thing causing that depolarization. But once you hit peak 5, the voltage gating channels are all the way open, allowing the potassium to enter in. And the potassium doesn't have that inactivation gate. It only has the activation gate. And whenever that opens, it's going to allow the potassium to leave the cell, making this gradient, making the cell more negative, which which we see at 0.6. 0.6, all the voltage gated channels are all open, which is causing that repolarization or the falling phase, also known as. Once you get down far enough, you're going to reach the threshold again. Once it reaches that threshold, the voltage gated potassium channels close slowly, and due to its slow closing, it's going to cause it to actually go past RMP a little bit. And that RMP is going to be, and going past that RMP is going to be known as hyperpolarization, number 8, and which becomes slightly more negative. But then our sodium potassium pump helps restore that RMP, which is why it doesn't just stick down here at the bottom, it moves back up there. Next, we're going to talk about graded potential and action potential as well. But before we do, I want to discuss a little bit about temporal summation and spatial summation. So I drew here the difference in different colors. So we have our soma right here, our neuron soma, which is its entirety, and the entirety of this thing right here, like right just at this end. Then you have your dendrites right here. You have your axon hillock right here. It's a CK. And then you have an axon right here. So showing this what spatial summation is and temporal summation. As you see in orange, these numbers right here, these are the signals that are being sent down through this same location, which is exactly what temporal summation is. That is going to go, the temporal summation is going to beef up that stimulus all in one area, while spatial summation is going to beef it up in multiple different areas. As you see in red over here, those signals, you're getting multiple signals just at a bunch of different locations, but it's still within the same neuron. So knowing the difference is, with that, I want to talk about graded potential and action potential. Graded potential varies with the stimulus. So you can have a graded potential go here and then back down, or make it to the action potential and then allow the action potential to take place. So each one can have different levels based on the stimulus that is being hit with, and they can be summated together. Like I was drawing earlier, you can see a wave that reaches up to threshold and it reaching there. While in action potential, you can't have that. There's no summation whatsoever. As you see, whenever the action potential takes place, which is after that threshold right here, you don't see any summation whatsoever. And it's an all or none principle. If you reach the threshold, great, you have an action potential. If you don't reach that threshold, you will not have an action potential, period. There's nothing you can do to start that without reaching that threshold. All right, next thing we have up is give an explanation of capacitance and length constant. Describe how capacitance and length constant are affected by myelin. So let's first go into capacitance here. I drew the equation of capacitance, which is capacitance is equal to Q over V, which Q is the number of charges separated, such as like over here we have 6 negative charges, 6 positive charges, over V. V is equal to the potential energy of negative and positive charges coming together if the membrane was removed. Now let me explain that in a little bit more depth. Let's say you have a membrane here. This is your thickness of the membrane. let's say you have a thick membrane here, you have a negative charge here and a positive charge here. If you remove this membrane, this positive charge and negative charge are going to come together with a force, right? Now, if we have a larger membrane, you have a negative charge and a positive charge here, and you remove this membrane, that potential energy, their force, is going to be even higher. And so that's what that voltage is. That voltage is going to be that it's going to be the thickness of the membrane is going to be that potential. The voltage is going to be that potential energy of the positive and negative coming together. We also know that it's equal to the permittivity of the area over the distance. And so we see here, we talked a little bit about the permittivity, in which your permittivity is going to increase with the smaller axons and decrease. This one's slightly less permittivity than this one. It's going to slightly decrease as it gets bigger, and then if you have myelin, we'll talk more about that here in a minute, it's going to decrease the most because that permittivity is very low. And then the area in which it can cover is like the area of the membrane over the distance that they are. So if the capacitance is lower, then you need to move less charges to depolarize the membrane, causing a faster action potential. So the less charges you have, the faster you can do an action potential. And we'll talk about that a little bit more here in a minute whenever we talk about the time constant as well. Just real quick to teach you about membrane resistance. Membrane resistance is basically the inverse of permeability. So if you have a higher membrane resistance, you have lower permeability. And conductance and permeability are the same thing, really. So with this being said, we can jump into our length constant equation, which length constant is equal to your membrane, the square root of your membrane permeability over internal resistance. Now let me teach you a little bit about internal resistance. I drew a little axon here with a neuron here with the axon. And this positive charge is going to have an effect down through the axon. And so it's going to put forth a charge that moves across the way. If there's nothing blocking that way, it's going to be able to continue moving further. But let's say that you have something like a negative protein in there. It's going to decrease, it's going to increase your internal resistance because it's blocking that. We call it Bwong in class, but it's that repulsion, that positive charge electrical field that is moving down the way. So you get a smaller electrical field that is moving. Now let's say you have a smaller axon. That positive charge is going to be able to send that electrical field a lot further. So therefore it's increasing, that's decreasing your internal resistance. While having something in the way or having something higher is going to increase your internal resistance. Yeah, so if you have something smaller and something negative block away, it's going to have higher internal resistance than if it was smaller, because that Buang, that electrical field, could still make it through while this one would stop. With that being said, now we know that length constant, how far that electrical field can travel, is going to be based on that membrane resistance and the internal resistance. Because if that membrane resistance is opening up at each place, like there's more channels, if the membrane resistance is, if we have the higher membrane resistance, we're going to have a higher length constant because there's not going to be as many things taking away from that charge. So that this will be able to travel much further. So we talked a little bit about capacitance and length constant. Now let's talk about how it's affected by myelin. Real quick, before I do, I just want to talk a little bit about time constant. Time constant is going to equal your capacitance times your Rm. So if you have a larger axon versus smaller axon, the time that it's going to take, if you have a myelinated, we'll get to time constant actually after I teach about myelin. So here we're going to discuss a little bit more about the electrical charge. So the electrical charge of a non-myelinated axon is going to be taken up by the negative charge on the inside of the cell. So this negative charge is going to take up some of that electrical field that the positives have, and they are going to allow more positives to be next to each other because that electrical field is not repulsing each other as much. But now, as we see with the myelin is basically made up of lipids. It's the myelin sheath, which is made up of Schwann cells. And that lipid is going to put more space in between the negative and positive charges. So therefore the negative electrical field cannot counteract that positive electrical field, which is going to mean that the positive electric fields are stronger than what they were over in the normal. So with that happening, it's going to push these positive charges away, and you can't fit as many positive charges in, which reminds me a little bit about going back here to capacitance. Capacitance is the ability to fit more charges, because if you have that on the normal axon, if those charges, you are able to fit more as there's less electronegative field there. But with a myelinated sheath, that electrical field is much greater. You can't fit nearly as many positive charges there. And that's our capacitance, is being able to fit charges on that wall to be able to match with the negative charges. And so going back to how it's affected by myelin, is that length constant is going to have a greater membrane resistance, because as you see here, we can have channels in the normal receptor right here, but when this lipid, you can't have the channels where the myelin is, so you're increasing your membrane resistance, which altogether will increase your length constant. Another thing to note is myelin sheaths are generally on larger axons that are larger. So your Ri constant is also going to decrease because it's larger. So that way, it's going to increase a little bit, but not enough to counteract this Rm. And with the myelin sheaths, we're just going to draw 2 here. Whenever an action potential occurs, that sodium is going to rush in, causing a positive to be here, and that's going to increase your length constant, and your electrical field can then jump straight over here, pushing that spiraled amino acids up, opening up your gate, allowing for the next action potential to take place and move faster down the field. So teaching about, because you can fit less positive charges out here, it's going to move faster down, which is why our time constant equals capacitance times Rm. So Rm may go up, but it's a lot smaller than what our capacitance is, because our capacitance is a lot lower due to all this myelin, which causes our time constant to become low, allowing the action potential to make its way down really fast. So if we take away that myelin, then that capacitance will be higher up here, and it has to start filling these charges a lot more in between each one. And so therefore it's going to take more time to travel down that axon. So that finishes up our understanding of, and between each axon, myelin sheath is what we call the node of MVA. That's the position in which it's located. And so that finishes up our discussion here, and I'll briefly touch on how the positive charges will bounce off of each other in succession to cause this gate to open even quicker, which is what we call saltatory conduction. As those positive charges bounce off of each other, they will push those gates open, causing for that faster action potential. Thank you for watching. We'll go ahead and end with a dad joke. So, why is it so cheap to throw a party in a haunted house? Because the ghosts bring all the booze. You're welcome. Have a great day.